So our first emergent property of water was cohesion. And what exactly does cohesion mean? Well, it says cohesion is the bonding of a high percentage of the molecules to neighboring molecules. So basically what that means is when somebody uses the term cohesion, they're referring to the ability of water molecules to stick together. If you think about it, when you drink some water, you don't want to drink one water molecule and then go find another one and drink that, right? That wouldn't be very efficient. So water molecules need to cling together, and the way they do that is through this process called cohesion. And then the way they specifically bond to one another, again, is through that hydrogen bonding we described earlier. So this cohesion is really helpful, not only for us, but for different types of plants and tall trees that need this water to survive. So here's an example of a large tree that you might find. As you could imagine, trees bring in water through their roots. And if you go on to take biology 2, you'll learn about all these different water conducting cells that can bring in water and supply the leaves that may be hundreds of feet up in the air with the water that they need. And so again, it's important that this water stick together, or the water molecules stick together, so that they can be transported to the top of the tree. And in a minute, we're going to talk about another method of how trees bring water up to their leaves, and that's called adhesion. So, adhesion sounds pretty similar to the word cohesion, except for there's one difference. Adhesion is actually the clinging of one substance to another. So, in our example, we're talking about water molecules. So, if we go back to our tree example, we can wonder, or we might wonder, all right, well, our water molecules are sticking together through this process called cohesion. But how is the tree actually going to grab a hold of all those water molecules? Well, what it's going to do is bring the water up through this method called adhesion. And what I mean is that those water molecules are going to grab on to the cells inside the tree. And the process of those water molecules kind of bonding to another substance, in our example, the tree, is this process called adhesion. So the adhesion of water to the walls of the cells in plants helps counter that downward pull of gravity it's going to experience. And therefore, our really tall tree can bring water from its roots all the way up to the leaves that may be hundreds of feet in the air. Now, when talking about water, another thing you have to consider or just mention is this thing called surface tension. And everybody's probably heard of that, and you know that if you've gone out to a pond or you sit on the edge of a river, you can see leaves floating down the water. Okay, so why don't they just, break the surface and sink to the bottom? Well, water tends to have this kind of invisible film over it, if you will, and that's what we refer to as surface tension. But technically, the definition they give it is a measure of how difficult it is to stretch or break the surface of a liquid. So this kind of, again, makes water behave as though it has this kind of coating on top of it. Another example might be if you lay a needle sideways down on top of the water. It's going to stay there. It's not going to sink underneath the water unless disturbed because of that surface tension. This little critter's kind of cool. This is a water strider, and you'll see these in ponds and wetlands, and what they do is they basically kind of scamper across the surface of water, and again, they're able to do that because of that surface tension. Now, the second emergent property we discussed when we were talking about the four main properties of water was the fact that water has the ability to moderate temperature. So here it says it does that by absorbing heat from air that is warmer and releasing the stored heat to air that might be cooler. So I like to use examples. So let's use an example here. We're pretty close to the beach, so lots of us might like to drive a couple hours and go relax on the beach. And one thing you might notice when you go down there is the climate or the air temperature always seems to be a little bit more moderate or more consistent than it might be if you go farther inland. So it's definitely going to be more consistent than if you went all the way to the Midwest or someplace like that. And the reason for that is because of the fact that there's so much water around. So what happens is that, let's say winter's coming to an end and it's starting to warm up outside. Well, as it starts to warm up, it may not seem like it's warming up quite as much at the coast because all that cool water is going to absorb some of that heat from the air into the body of water itself. And then if you look at the reverse of that, you can kind of see how it works itself out there. So as it starts to cool off outside, that water that's kind of warmed up is going to start to release that heat into the cool surrounding air. Now, heat and temperature are something that can be kind of commonly confused. But before we kind of distinguish those two terms, we have to first mention something called kinetic energy. And kinetic energy is considered the energy of motion. So I always think of somebody jogging outside. If somebody's running, right, they're moving. So they're utilizing this thing called kinetic energy, or the energy of motion. Now we can apply kinetic energy to this kind of term we use that we call heat, right? And really what heat is it's a measure of the total amount of kinetic energy due to molecular motion, right? So when you heat up a pot of water, those molecules are going to start to move faster and faster. So we could determine the heat based off of how much kinetic energy was going on within those molecules. How quickly are they moving? Now, temperature is actually how we measure how intense heat is, right? So temperature measures the intensity of heat. So while heat is kind of the amount of kinetic energy that's going on, temperature is our way of kind of quantifying how hot something may be. Now, water has high specific heat, and this can be kind of confusing to people when we talk about the specific heat of a substance, and I don't want you to get too caught up on it. But we have to kind of have a standard to where we can kind of compare, other things against it. So here it says the specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. So if somebody's studying the specific heat of maybe a chemical reaction, or, there's all sorts of different experiments somebody might do with this, they're going to use the specific heat of a substance as kind of a standard to compare their results to. So I really just want you to be familiar with the fact that scientists that might be studying kind of heat transformations or heat reactions are going to be comparing it against this 1 gram of heat that has to be absorbed or lost. And again, I like examples. So water has a high specific heat, which allows it to minimize temperature fluctuations to within permits that permit life, right? If you're living, you can't get too hot, you can't get too cold. The human body, or, any animal body or living organism requires a certain range of temperature to survive. So here it says on the very bottom of the page, there's 2 bullets, and it says heat is absorbed when hydrogen bonds break. It also says heat is released when hydrogen bonds form. So a specific example that we can kind of compare this to is when we are in the kitchen and we're going to boil some water. So everybody's done this. Everybody can kind of relate to this example, but you take out your pot and you put water in it and you set it on the stove. As your water starts to get warmer and warmer and that kinetic energy is increasing because those little molecules in the water are starting to move faster and faster, eventually we start to see these bubbles form when the water starts to boil. So what's happening there is that more heat is being absorbed, and because of that, those hydrogen bonds between our water molecules are starting to break. And those bubbles we see are actually the oxygen molecules being released. Now, let's say we've finished boiling whatever it is we're cooking, and we turn off the burner. What happens is that water is going to start to cool back down, and we're going to see less and less of those bubbles forming. what's happening at that point is that heat is going to start being released, right? The water is getting cooler, so the heat that was within our water is being released, and those hydrogen bonds are at that point going to start forming again. So that's what they mean by heat is absorbed when hydrogen bonds break, and heat is released when hydrogen bonds form. Now, evaporative cooling is something else we can kind of relate to. So let's give a definition to evaporation real quick. It says evaporation is the transformation of a substance from a liquid to a gas. Okay, we're all familiar with that. If you take a bucket of water and you put it outside, you come back a couple days later, you're going to notice that there's less water in your bucket. And that's because of this process we call evaporation. So again, if somebody's studying the rate of evaporation or the heat of vaporization of, a substance, they have to have something to compare their experimental groups against. So they developed this heat of vaporization, which they describe as it's the quantity of heat a liquid must absorb for 1 gram of it to be converted from a liquid to a gas. So again, they're just using that 1 gram as kind of the standard with which they can compare their results. And evaporative cooling specifically is due to water's high heat of vaporization. Okay, and so it allows water to cool a surface. So if you think about that, if you're outside and maybe you're exercising or you're just exerting yourself, you're going to start to sweat. So the surface of your skin is going to have a liquid layer on it. And what happens is that through evaporative cooling, that liquid is going to eventually be turned into a gas. And what happens is that those hotter molecules are going to evaporate first. So you're losing that heat more quickly, which allows you to cool off, or allows the surface of your skin to cool off.